When you receive a new data set, the first step in the process of analyzing the data is to create some graphs to help you get a better understanding of the information that you have in front of you. The next step in your analysis will be to create some numeric summaries of the data as well. The goal of this process is to understand the distribution of the data and to be able to identify any unusual observations or patterns of interest that might give you a clue as to what else you want to do with your data moving forward. The first aspect of the distribution we want to understand is the center or the central tendency of that distribution. And there's several different measures of center that we could consider. For this course, we'll primarily be looking at the mean, the median, and the mode, but I'll also briefly mention the trimmed mean and the weighted mean as they sometimes have application in very specific scenarios. The mean is the most common measure of center. And the mean in the context of statistical analysis is exactly the same as the mean that you are familiar with, which is just the simple average of the data. So what I want you to remember for this course, beyond just the way of computing the mean, is that the mean is the preferred measure of center for data with symmetric distributions. We've talked about the shape of a distribution, that it can be symmetric or skewed, and when the distribution is symmetric, the mean is a very good estimator of the true center of the distribution. However, the mean is very sensitive to outliers, and it's sensitive to skewness in the data. So if you have a data set that is highly skewed or that has outliers that are occurring in the data, then the mean may not provide an accurate representation of the center of the data. We use the notation x bar to represent the sample mean, and the sample mean is the point estimator for the population mean, which is represented by the Greek letter mu. As a reminder, here is the formula for the sample mean. It simply is the sum of all of the observations of interest divided by the total number of observations in the sample. The median is another very common measure of center, and the median is just the center value in the data set. Or in other words, the median is the value such that 50% of the observations are greater than the median and 50% of the observations are less than the median. The median is going to be your preferred measure of center when dealing with data that are skewed or that have extreme values or outliers in the distribution, whereas the mean will be strongly impacted by skewness and outliers. The median is very robust to these types of anomalies in the data and will continue to stay true to the center of the distribution even when outliers and skewness are present in the data. To compute the sample median, you simply sort the observations from smallest to largest, and if you have an odd number of observations, the median is just the center value in the data set. If you have an even number of observations, again, sort from smallest to largest, but now the median becomes the average of the two middle values. For the purposes of this course, we're not going to be computing the mean or the median by hand. Instead, we'll be using Excel and the functions available in Excel to compute these statistics. There is an additional interactive tutorial that will lead you through the process of identifying and using the proper Excel functions to compute the mean and the median, as well as the other sample statistics that we'll be discussing in this lesson. So let's recap. Suppose that we have a symmetric distribution. For a symmetric distribution, the center of the distribution is right here in the middle, and both the mean and the median will be accurate representations of that central part of the distribution. So the mean will be close to the center, the median will be close to the center. Both of those will work well. Because the mean is typically the most common measure of center that people are familiar with, we typically will choose the mean for symmetric distributions. However, suppose now that we had a distribution that looks something like this. It has outliers, maybe that are very large. So something like income, where the majority of people have incomes that are in the left-hand side of the distribution, but maybe there are a couple of very wealthy entrepreneurs who have very large incomes and they're out there in the tail of our distribution. In this scenario, the center part of the distribution is still over here near the middle of this bulk of the data. However, for the mean, what happens is the mean gets inflated by those large values. If you think about it, if you take the mean, what's going to happen is the numerator is going to become much, much, much larger as you add those big values in, the denominator isn't going to change much. So instead of being here towards the true center of the distribution, the mean gets pulled towards those outliers, and it's no longer a good representation of the center of the distribution. On the other hand, if you have the sample median, if you think about these data here, the median ranges from 12 up to 30. But if we were to add just one more observation, an outlier, say, that had a value of 500, rather than becoming much, much larger, the median will just essentially shift over one box, and so the median for that new distribution would only be 26. It wouldn't change too much from the median of 22.5. So the median is very robust to outliers, and when you have a scenario where the distribution reveals outliers, either very large or very small outliers, the median is going to be the best representation of the center of the distribution. Another scenario to consider is the scenario where you have a skewed distribution. With a skewed distribution, a similar thing happens. The center of this skewed distribution really, truly should be somewhere in this neighborhood. However, when you have this long tail with these larger observations, what happens is that the mean, again, gets pulled in the direction of that tail. So instead of being here in the true center of the distribution, the mean gets pulled towards the tail. It's overinflated or underinflated, while the median stays closer to the true center of the distribution. The median is not bothered by that skewness. So if you have a distribution that's symmetric, you should choose the mean as the preferred measure of center, and if you have a distribution that is skewed to the left or to the right, or a distribution that has some extreme values or outliers, the median is going to be much more robust, and the median will be the best measure of center, or the preferred measure of center. And that's what I really want you to remember. It's simple to compute these quantities using Excel. However, we want to be sure that we're using them in the right way and with the right data, so that we provide the best representation possible of the center of the distribution. Another common measure of center is the mode, and the mode is useful primarily because it can be used to describe categorical data that is not numeric. And so the mode is the most frequently occurring value in the data set. It's typically the tallest bar that you would see in a bar chart. It's not as useful for interval valued or numeric data because you may or may not have one value that's most frequently occurring, but it is the one measure of center that can be used to describe nominal data, so we want to make sure that we're aware of the mode. The trim mean is very useful if there are extreme values in the data set. So an example of this where the trim mean is often used would be with financial data. So suppose that you are looking at checking account balances, and perhaps you have some checking account balances that went negative at some point when the accounts were overdrafted. You may want to ignore those overdrafted account balances and only look at the account balances that are in good standing. You might trim the mean by removing all of those observations that are less than 0, and then computing the mean based on the remaining data. So the trim mean is used quite a bit in financial types of computations. So I just wanted you to be aware of that, but it's not something we'll be focusing on in this course. Similarly, the weighted mean is computed based on the importance of each observation. So each observation does not receive an equal weight. For example, if you're looking at computing your GPA, the weights might be the number of credit hours. So 3 credit hour course will carry more weight for the same grade than a 1 credit hour course. And to compute the weighted mean, you simply sum up the values times their weights and divide by the sum of the weights. Again, the weighted mean is not a statistic that we'll be spending a lot of time on in this course, but you should just be aware of it for completeness. So let's look at an example and compare these measures of center so we can understand what they're telling us and how we might use them. And we'll carry this example through for measures of spread as well. This particular example is looking at a supplier to the Levi Strauss clothing manufacturing plant. The goal here is to make sure that we're minimizing waste. And so waste is what happens, is the amount of fabric that is not used because the pattern is not laid out properly on the fabric. So in other words, as you see at the bottom of the screen, if you have patterns for clothing, you can lay them out in different ways on a piece of fabric. Some ways are more efficient than others. The assumption here is that a computer layout, a computer-generated layout, will be the most efficient. And so if an individual employee who is doing the pattern layout wastes more fabric than the computer, if there's fabric that is left over beyond what the computer would have had, then we consider that to be waste or run up. However, it is possible that the employee can beat the computer because some of these employees have been doing this for a very, very long time and they know exactly how to get the most out of a piece of fabric. And so a negative value would suggest that the employee did a better job than the computer in controlling waste. Your goal, if it's the quality control manager, is to try to determine if there are plants that we should be concerned about, plants that we might want to drop, or that we might want to go back and take some remedial action to help improve their quality standards. And so you've collected data from these 5 different plants on the run-up that's being produced during the course of production, and we want to look at those data to try to understand what they're telling us. So if we go to Excel, here are the data, and you have this spreadsheet available to you as well. We see the 5 plants here, and we notice as we look at the plants a few different things. First of all, if you look at plant 1, you'll see that most of the values are 1 or 2, maybe 3, but we have some values that are, for example, there's a 47, that's a relatively large value, a 19. So there's some outliers in plant 1. Similarly for plant 2, right, we have some outliers in plant 2 as well. Plant 3, plant 4, plant 5, we see a little bit more variability in those data, so there's some bigger values, but they're kind of interspersed throughout, so they don't seem to have as much of an issue, but definitely plant 1 and plant 2 have some outliers or some unusual observations. When you're faced with this in real life, what you would actually do would go back to the original data to try to determine why those values are in there. Was there a problem on that particular day with the plant or with the manufacturing process, or perhaps, given the scale of these data, were these values entered incorrectly? Did someone put a decimal place in the wrong spot? So instead of being 42.7, we should have 4.27, which would be more in line with the values for plant 1. Or instead of having 70.2, we have 7.02 or 7.2, which would be much more in line with the values for plant 2. So the first step in an analysis, if you see outliers or unusual observations, in a real-life scenario you would investigate those. But because we don't have that opportunity, we're going to assume that these are real legitimate values for the waste for plants 1 and 2. So we can compute our summary statistics. We're going to do that using the Data Analysis Tool Pack, which you'll get the chance to explore in your interactive tutorial. And we can see that we've computed here a number of different statistics. In particular, here is the mean and the median for each one of those plants. So the first thing I want you to notice is that for plant number 1 and for plant number 2, the mean and the median are very different. In particular, for plant number 1, the mean is 4.52 while the median is 1.95. That difference we're seeing is due to those outliers, right? Again, if you look at the raw data for plant number 1, there's some negative values in there. We have some employees at that plant who really know what they're doing, so we have some negative values. We have some very small values like 0.3. 1.3 and so forth. So for the most part, plant 1 seems to be doing a pretty good job, but because of those outliers, the mean is being inflated. It's much larger than probably where the true center of those data should lie. Similarly for plant 2, we had in particular that one really large outlier, and so we're seeing that reflected in the mean. Conversely, if we look at plant 3 or plant 4, for example, where we didn't have any outliers, you can see that the mean and the median are very, very close for those, and fairly close for plant 5 as well. Okay, so that is something to be aware of. If you have not created a graph of your data and you see a big discrepancy between the mean and the median, that is indicative of the fact that there is some skewness in the data, or there's some outliers or unusual observations there, and you want to be cautious in using the mean because it may not be a true representation of the actual center of the distribution. With respect to these data, if our goal is to minimize waste, then as we look across these plants, we might begin to hone in on plant 1 or plant 3, both of which seem to have relatively low waste. Plant 1 might actually be the lowest if you look at the median value. The mean values are pretty close for those two plants. We might be almost ready to write plant 5 off because plant 5 does have a very large value for average waste. Plant 4 is also relatively large. Plant 2 is not quite as obvious because of the outliers, but we can begin to start to make some choices about which plants seem to be doing the best in terms of minimizing waste and which plants seem to be a little suspect that we might want to maybe do a little bit more investigation. However, minimizing waste may not be our only concern. We may also be concerned about consistency. So we see the waste values for these plants, but we might also want to ensure that we're getting pretty much the same product every week whenever they do their work. And so in addition to understanding the center of the distribution, we may also want to understand the spread of the distribution. How much variability does each one of these plants have in terms of its waste, and how might that impact our ultimate final decision? Measures of spread will be the subject of the next video lecture that you'll watch.